Session. Oh. Hello, sir. Hello, sir. Uday Maitra, sir.
Yes, hello.
Welcome, sir. How are you, sir?
I'm good, thank you.
Yeah, sir, do you want to check the PPT?
Yeah, sure. Let's do that because I'm also going to play some videos. So let's check if the audio plays all right.
Okay.
I'll share my screen with the sound. Let's see how it works out. Okay, I hope you can see my screen.
Yeah, yes, sir. Yes, sir. Your screen is visible.
This
Yes.
is my first page of my PPT.
Okay.
I'll make it full screen. And
Yeah.
I have a test video. Let me click here and see whether you can hear the sound and the video.
Sure.
It will be on the top left.
Right. It's audible and visible.
Audible and
visible. Yes. Yes.
Excellent. So I will also show whether see whether you can see my
Yeah. It's zooming. When you move the cursor, it's zooming.
It's zooming, right? And
yeah.
I'll show the okay. So the zooming is okay, and here you can see my laser pointer.
Yes. Yes.
Excellent. Excellent. And this is the spotlight. Okay, excellent.
Yes. Working fine.
So I will stop sharing it now and then get ready for the.
Yes, we will start the session exactly at 2 o'clock.
Sure, thank you.
Yes, sir.
Hello. Hello.
Sir.
ಹಲೋ ಹಾ ಹರೀಶ್ ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್.
Good afternoon. Welcome to the second session of the Faculty Development Program. The speaker of the second session is Professor Uday Maitra, Department of Organic Chemistry, IISc Bangalore. Sir, will be talking on learning chemical principles through simple experiments. I request Dr. Vibha Vinay Kumar Bhatt to kindly introduce the speaker and moderate the session. Thank you.
Good afternoon, one and all present here. So it gives me an immense pleasure to introduce our eminent professor, Professor Uday Maitra, Department of Organic Chemistry, Indian Institute of Science. After his BSc from Presidency College, Calcutta, and MSc from IIT Kanpur, Uday Maitra received his MPhil and PhD from Columbia University in 1986, working with Professor Ronald Breslow. Following a postdoctoral stay at University of California at Berkeley with Professor Paul Bartlett, he returned to India, and after a year at IIT Kanpur, he moved to IISc Bangalore in 1989. His research interests are in the chemistry of bile acids, hydrogels, metallohydrogels, and organogels, organic inorganic hybrid materials, photoluminescent sensors, etc. His group has recently developed a general strategy for low-cost paper-based photoluminescent sensors for enzymes and biorelevant small molecules. He is also greatly interested in chemistry education and is a regular participant in a variety of outreach programs for high school and undergraduate students. He has received a number of awards and honors, including the S.S. Bhatnagar Award in Chemical Sciences in 2001, and is an elected fellow of the Indian Academy of Sciences and the National Science Academy. I welcome you to this session, sir, and I hope all our participants will be highly enriched by your talk. We welcome you, sir. Thank you.
Thank you. Thank you, Dr. Viva, for the very generous introduction. I would also like to thank Dr. Ashley for the invitation to participate in the faculty development program, and also to give me the flexibility to speak on something which may not be directly connected to spectroscopy. In fact, Professor Shiva Prasad in the morning has set the stage for what I would like to speak this afternoon. And this will be on using experiments, simple experiments to teach chemistry principles. In a sense, what I'm going to do is to kind of expand on what the previous speaker had talked about and apply the principles to explain things in different ways to students using a slightly different strategy. You know, for, as he mentioned, as Professor Shiva Prasad mentioned, that you need to develop new ways of explaining the same thing to students and make it attractive to them so that they get thirsty when you take them to the pond for drinking. So I will take that strategy today. And at the end, towards the end, I will touch very briefly on a very specific aspect of spectroscopy. Now, today, power is playing hide and seek in the institute. So what I will do to save battery power and everything else, I will stop the video for some time till I show the experiments. Let me stop the video and share my screen with audio so that you all get to see what I am speaking. And let me go to the second slide because we have already tested the video. So this is basically my plan, is to highlight the importance of learning chemistry through simple experiments. Some of the experiments I'm going to show you are appropriate only for the students who are present in the audience. And but perhaps others will also get a little bit of fun out of it anyway. So just for the students, I have one simple experiment, and this is the classical reaction between hydrogen and oxygen by bursting hydrogen balloons. Basically, what I would like to show by this experiment is that whatever experiments you want to show in a chemistry lab or in a public place must be done with appropriate safety. And in this particular case, since you are burning or bursting hydrogen balloon, essentially exploding hydrogen balloons, they should be at the end of at least a 5 to 6 feet long stick, and the candle that you're going to light it with should also be at the end of a long stick. And then you can enjoy the experiment and in a safe way. Okay, so this is a very simple experiment where you can demonstrate to primarily younger students, and then you can ask them questions about gas law, about how much water will be produced in milliliters if you burn a certain volume of hydrogen gas, and so on and so forth. Another experiment that I frequently show, again to children of a younger age, is about magic writing, but it uses principles of inorganic chemistry, principle of complex chemistry. And that is, this is the way the experiment is done. A couple of my students, you can see, are holding a banner. Nothing is visible on the banner, but I have something in my hand. Just a second. Something in my hand. Let me get my laser pointer. And I will spray this liquid on this particular banner, and then quickly we'll see This is from a different day. That's a nice, message comes on the banner. And what you notice is that there are two different kinds of colors which are produced, even though I use only one liquid to display the colors. And the chemistry is not very hard to understand. So the colors which turned blue were written with potassium ferrocyanide, whereas the colors which turned maroon were written with potassium thiocyanate. And what I sprayed on the banner was ferric chloride. And that basically let the color come out. And then using this experiment and experiments in which you can develop, other types of letterings, other combination of chemicals, one can teach a lot of principles about complex chemistry. And again, this is applicable perhaps for the undergraduate students and high school students. One of the points that the previous speaker also highlighted is about the importance of asking questions. As he also mentioned that most of the time, our students are busy answering questions, but it is asking questions that can lead to better understanding of the subject. And again, just for the students who are in the audience, let me show you a statement made by a very famous person. And he said in his in some interview that his mother made him a scientist without ever intending to, because he went on to say that whenever he would come back from school, unlike other mothers who typically ask, "What did you learn today?" His mother would not ask that. His mother would ask, "Did you ask a good question today?" And then he goes on to say that difference, asking good questions, made him become a scientist. And who is he? He was I.I. Rabi, who got the Nobel Prize in Physics in 1944 for his resonance method for recording the magnetic properties of atomic nuclei, basically which is nothing but nuclear magnetic resonance. And I'm sure that Professor Madhu, a couple of days later, will say a lot about NMR to the audience as part of the spectroscopy program. Okay, one of the things that I would like to do is to start with the periodic table. And this is a slightly different version of periodic table, which many of you may not have encountered. So I thought I will give you a brief introduction to this. And this is a periodic table that was launched by IUPAC in 2016. And this is called isotopesmatter.org. So I would encourage all of you, students and faculty, to take a look at this particular website, because here, not only the elements, but also the use of the isotopes has been fairly nicely described. And there are many examples shown in this one, that why isotopes matter, what kind of things that you can do by isotopic isotopic studies, and so on and so forth. And I will not go into the details of the website because that's not the purpose today, but just to mention that there are examples of various types of useful information that people have obtained using isotopic studies of different types. And what I would like to do is to start with a simple experiment of the most common isotope that we all are familiar with, and that is deuterium oxide. And deuterium oxide, as all of you know, is known as heavy water. And that is because it has a higher density compared to water. And I'll just show you one of the effects of D2O in biological systems. And because many students ask that, whether D2O is actually good for our health. And a quick answer is that it's not, because the biological system is our metabolism is a very complex process. And it has evolved over millions of years using H2O as the liquid, as the medium. So any changes you make in the medium will have an adverse effect on the metabolism and on the growth. And that is very nicely shown in this particular slide. You see what here on the right-hand side is a tobacco plant grown in water, that is 100% water. And progressively you use 30, 50, 60, and 70% D2O, and you see that the growth of the plant has been severely retarded by this process. And clearly this is something that affects the metabolism, and it is because of a complex phenomenon collectively known as kinetic isotope effect, which is very useful for studying rates and mechanisms of chemical reactions. But the question that I have from this is that, okay, this is the reason why D2O is called heavy water. It has a density of 1.1. Water, of course, is close to 1. So the question I frequently ask is that, can you devise an experiment to distinguish H2O versus D2O, given the constraints that I will give you, or you will have only small amount of D2O, just about 3 milliliters, and 10 to 15 rupees for buying anything that you need, and simple apparatus that you can find in a high school laboratory or even in a kitchen. All right, so since we cannot have any interactive session here that easily, so I will show you the answer. And typically what I do is that I freeze a sample of H2O and a sample of D2O in these little syringes, 5 ml syringes, and color them differently. Okay, so one of them is H2O, one of them is D2O, and I don't know which one is which. Let's assume that I don't know. So the way to do it is to take a measuring cylinder, fill it with ice cold water, and of course all of us know that H2O ice will float on H2O. Similarly, D2O ice will also float on D2O, but it turns out that D2O ice is slightly heavier than H2O. And therefore, if I drop these two ice pieces in ice cold water, I'll tell you why ice cold water, then one of them will float, which is obviously H2O, and the one which will sink is D2O. And let's see what happens. And what happened in this particular experiment, you see that the orange ice, which I had on my left hand, is floating, whereas the other one, the green ice, has sunk to the bottom. So clearly there's a density difference. One is floating, one has sunk. So this is D2O. And the reason we use ice cold water is because you may not have noticed in the previous slide that, well, while H2O, of course, melts at 0 degrees, D2O ice melts at 3.8. So by keeping it in ice cold water, this one stays as ice for a much longer time. But then eventually what happens is that, let's expand the bottom part. After a few minutes, part of the D2O ice melts and it produces liquid D2O at the bottom. And now you see D2O ice is floating on D2O. Okay, so D2O ice, of course, is indeed lighter than D2O, but it is heavier than H2O. So this simple principle can be explained by showing this very simple experiment. This is a much easier experiment to do and much better experiment to do than simply measuring the density. Of course, you can measure the density of these two liquids and find that one is more than the other, but that's not a very exciting experiment. All right. Okay, so this particular slide is just to, again, point out to the students that, one of the features of your mobile phone is that the smartphones use as many as 40 to 45 different elements, and a great many of them are actually lanthanides, the so-called rare earth elements, okay, which are present both in the electronics and also on the screen. And the message I would like to get across to you is that many of these elements that we use on mobile phones are actually getting depleted, and there are some indications that many of them will not exist towards the end of the 21st century. All right, so let me go back to the presentation on chemistry in particular. So this is again an experiment on chirality, and I won't be able to show you exactly how the experiment is done, but just to give you a broad introduction, that we all have studied that a carbon atom, tetrahedral carbon atom, having 4 different substituents is chiral, because it does not superimpose on its mirror image. One of the points that I would like to highlight here is that if you have a phosphorus, a pentavalent phosphorus having the trigonal bipyramidal geometry, this is also chiral. This can be made chiral if I have 5 different substituents and under conditions that the trigonal bipyramidal geometry is stable. And I would like the students to do a little bit of a homework. And the question that I'm going to ask is that, as you know, that if you interchange any 2 substituents on a tetrahedral atom, it can be carbon, it can be anything else, as long as it is tetrahedral, interchanging any 2 pairs will give rise to a mirror image if all the 4 substituents are different. Can you apply the same principle?
Excuse me, sir. Uday Maitra, sir, your audio and video are stuck. Screen is not moving. Oh, it got disconnected.
Yeah, things suddenly went.
Uh,
Okay.
Yes, sir, we can hear you.
You can hear me now, yeah.
Yes, sir, sure.
For some reason, it went mute on its own. Okay, so here are examples which are frequently found in textbooks about.
Excuse me, sir. Sorry to interrupt you. Your screen is not sharing.
Okay, so I think, all right. Let me just go back. Something went wrong. I think maybe I got disconnected and okay, I will come back to this. 1 second, I have to share again. Yes, screen, share. Is it okay now?
Yes, sir. Now
Okay.
Yes.
Yeah, sorry for this interruption. I don't know. In between, power went away for a couple of times, but I do have a backup, so it should be okay. All right. So what I was trying to show you here is that these are 2 examples which are frequently shown in textbooks to highlight that enantiomers have different properties when they interact with another chiral molecule. For example, this is an example of limonene or limonene. The R enantiomer and the S enantiomer, their mirror image forms, they have the same physical properties except optical rotation. But when we smell them, they smell different. For example, R limonene smells like orange, whereas S limonene smells like turpentine or pine. A related molecule is shown here, which is carvone. And in this particular case, R carvone smells like mint or pudina, whereas S carvone smells like shah jeera, the small variety of jeera or caraway seeds, which are frequently used in things like biryani cooking. Usually when I have an in-person show for the chemistry experiments, I would normally bring samples, because I believe that in this particular case, it's not just seeing is believing, it is smelling that is believing. So I bring samples of these 4 so that the students and those in the audience can actually smell the samples and confirm that they are different. So in this context, I would also like to highlight one simple experiment on optical rotation. And of course, all of us know that chiral compounds in an enantiomerically pure form will rotate the plane of polarization of light. And for the students, again, I would like to show you the principle of a polarimeter. In a polarimeter, you typically have a sodium lamp which emits at 589 nanometer. And you put a filter that filters out all radiation except those, let's say, which are polarized in the vertical direction, as I have indicated here. Now, what do? You view the light from the other end, but through another polarizer, which is kept perpendicular to the first one. Now, if my eye is here and I look at the lamp, no light will pass through the crossed polarizers, okay? Because what is vertical cannot pass through a filter that is oriented in the horizontal mode. But if I now put a chiral substance in between, for example, if I put a solution of glucose, it will rotate this plane polarized light either to the right or to the left, depending upon whether my sample is dextro or levorotatory. Now, sugars are always D, and D-glucose actually shows a positive rotation. So what will happen is that once this light, plane polarized light, passes through the sugar solution, it gets rotated to the right. So if I keep this polarizer, the analyzer, in the same orientation, I will now see a little bit of light passing through it because it is now at an angle. So this one will now have to be rotated clockwise to get the light, to see no light passing through these cross polarizers. In other words, to get a null point, I have to rotate it clockwise. And that essentially will prove that it is a dextro-rotatory substance. But what happens if this light is not sodium D light, but it's a white light? And that is an experiment I would like to show in a video. And let's hope that
when plane polarized white light from an overhead projector is passed through a cylinder of sucrose solution, a spiral rainbow is observed perpendicular to the cylinder. When white light passes through a polarizer, the extent of rotation of light depends on its wavelength. Short wavelengths are rotated more than longer wavelengths. Because the wavelength of light determines its color, the variation of color with distance through the tube is observed. A second polarizing filter is placed on top of the cylinder and is rotated to display the range of transmitted colors. This dependence of specific rotation on wavelength is called optical rotatory dispersion.
Okay, so let me quickly explain using the same diagram what happened here. Instead of a sodium D lamp, I'm using white light, which has the spectrum of colors 400 to 700. And they will be rotated to different extents. So the blue light will be rotated more, red light will be rotated less. And therefore, by adjusting the angle of this particular analyzer, this polarizing filter, I can filter out blue, green, red, yellow, and all the different colors of the VIBGYOR spectrum. Okay, and that is something that is very nicely seen in the experiment that I just showed you. And this can be done very easily if you can get hold of a couple of polarizing filters, solution of glucose or sucrose, and a strong torchlight. Okay, so let me show you another experiment, which is also a fun experiment. It is not related to the elephant, but it is called elephant toothpaste experiment, which some of you may have seen in videos. This actually is an experiment on catalysis. And this catalysis is demonstrated by decomposing hydrogen peroxide. As you know, hydrogen peroxide is a thermodynamically unstable substance because it exothermically decomposes into water and oxygen. But it is a kinetically stable molecule. So in normal conditions, it will not decompose significantly to water and oxygen. But this process can be catalyzed by many things. Among them, a simplest chemical is sodium iodide. And if you add sodium iodide to hydrogen peroxide, it will vigorously decompose into water and oxygen. And that is the basis of this elephant toothpaste experiment, in which what you do basically is to mix hydrogen peroxide with liquid soap, so that the oxygen bubbles that start coming out after adding sodium iodide forms a foam and it comes out in the form of a toothpaste. Let me show you a video. It is not very professionally done, but it is from one of my experiments. And I will, oops. Pick up the audio here. Audio is not important. And I'll go to 1 minute and 20 seconds. So what I have is a solution of, I'm adding sodium iodide to a mixture of hydrogen peroxide and soap. And you see that the oxygen evolution has started and it is coming out in the form of a foam. And you can prove that it is oxygen gas by taking a lighted matchstick and putting it in here inside the foam. And even though it is wet, it has water, the matchstick will glow very, very nicely. And I will show you in this one. You remove the flame, you extinguish the flame from the matchstick and put it in the, and you can see the glow that is coming out, okay, because it is oxygen and that supports the combustion. And if you are using a larger piece of a glowing piece of wood, it will burst into flames. Okay, let me close this and move over to the next one. So this is a very nice experiment, but it is a very messy experiment because you generate a lot of foam which contains hydrogen peroxide. So there are some safety issues in terms of disposing of the reaction products in this case. Let me talk a little bit about chemical bonding, because after all, chemistry is all about breaking and making bonds between atoms and molecules. Periodic table is fine, but periodic table only shows you the atoms. So unless the atoms form a chemical bond, you don't really have chemistry. I have 1916 written here, and that is because perhaps you know that G.N. Lewis, whose Lewis dot structures, you know, all of us learned drawing the Lewis dot structures right from high school. So Lewis, in fact, came up with a very comprehensive understanding of the chemical bond, particularly the covalent bond, in a paper in 1916. So therefore, many people regard that that particular paper forms the basis of our understanding of chemical bonds. And one of the things that all of us have used in the past to show the bond between a small atom, which is represented by this particular small orbital in orange, and a larger atom whose orbital is shown here. And we frequently say that the orbital sizes have to match so that the bond is strong. In a sense, it is sort of like shaking hands. When the hands have very dissimilar sizes, you know, the shaking the hand is difficult. And indeed, if you look at a bond between a small atom and a large atom, such as nitrogen and iodine, the bond strength is only 38 kilocalories per mole. On the other hand, if the orbitals are of equal sizes, comparable sizes, the bond can be good because the handshake is strong. And such a bond, for example, between carbon-carbon, carbon-oxygen, carbon-fluorine, and I'm talking only about the single bonds, they are at least twice as strong as these weak bonds. Now, there is an interesting experiment one can do to show what happens when you have multiple weak bonds in a molecule. Perhaps you know that presence of a weak bond makes the molecule unstable, so it is energy rich, and such molecules can be used for obtaining energy in a short time. For example, all explosives, rocket fuels, all have many weak bonds. The ones, particularly the ones which have single molecule. I'm not talking about the combustion, getting energy out of combustion. It's a single molecule whose decomposition would lead to the liberation of a lot of energy. So the molecule we are going to look at is Ni3. And as I already mentioned, that a single nitrogen iodide bond is weak, and this particular molecule has a small nitrogen added to attached to 3 iodines, and clearly it packs a lot of energy. And let me show you an experiment to show how energy rich or how shock sensitive this molecule is. Again, this is a video.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
This is also an experiment that one can do on a small scale, but one has to be very careful about the way you prepare and store the Ni3, because it can decompose without much provocation, as you have seen that just by touching with a feather, it decomposes. So let's make the bond a little bit weaker, okay? Because this is a covalent bond, which we all know is weak, but there are other types of weak bonds, particularly the non-covalent bonds, and sort of one of the best among them is the hydrogen bond. Hydrogen bond, of course, is a sharing of a hydrogen typically between two electronegative atoms, and it plays a very important role. Again, sometimes, students, particularly the school children, want to know that why do we need to study about hydrogen bonds? And it's important because what you see here is the alpha helical structure of a protein, and on the right, it's a double-stranded DNA. And in each case, in this case, the alpha helix, in this case, the double helix is held together by hydrogen bond, in this case, between AT and GC, and here between the first turn of the helix and the next turn of the helix by NH and CO hydrogen bonds. So hydrogen bonds, of course, are very important in biology, but it's also important in chemistry. One of the fundamental properties that gives water its a liquid state is because of hydrogen bonds. Because ammonia is a gas, H2O is a liquid, and we frequently ask this question to high school students as to why this is so. And it is because in water you have a very dense hydrogen bonds. And a question that is related to hydrogen bond is why ice floats on water. Something that, of course, we did an experiment earlier with H2 and D2O. So it turns out that the ice has a much more open structure, as I show here on the bottom left, whereas in liquid water, it is a much more dense and more tightly packed hydrogen bonds. So when liquid water forms hydrogen bonds, let me see if this animation works on the bottom left. Yeah, it seems to be working on my system. You start with liquid water, which is much more condensed, has a high density, but once it forms ice, it opens up and volume increases. So one of the consequences of this, of course, is that ice has a lower density and is lighter than water. Now, water expands on freezing. This is something we all know. And many of us have done experiments by keeping water bottles in the deep freezer. And I'm going to show you an extreme experiment on this, in which water will be kept in an iron container and deep frozen. And let's see what happens. And frozen rather rapidly. Deep frozen is not the right word. Frozen very rapidly.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightly sealed. The bomb is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush bath. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides to burst.
Yes. So this experiment very clearly shows you that when you go from liquid water to ice, you lose a lot of hydrogen bonds. So even though one hydrogen bond is weak, But when you lose a large number of hydrogen bonds, that energy can be liberated with an explosive force if you freeze the water in a closed container very, very rapidly. I don't recommend doing this experiment though, because it's a bit too risky. So let's take a look at the next experiment, which is breaking a very strong bond. A very strong bond, for example, between carbon and oxygen, which has an energy of 190 kilocalories per mole. And this can be broken, in fact, by reaction with magnesium. And this is also a very unusual reaction. And I would like to show again a video on this.
Magnesium is placed in a cavity in a block of dry ice.
So you put magnesium on.
The magnesium is ignited.
On dry ice and ignite the magnesium using Bunsen flame and cover with another block of dry ice.
And covered with another block of dry ice.
So the burning magnesium has only dry ice surrounding it, no air, no oxygen.
Despite the absence of air, the magnesium continues to glow due to its reaction with carbon dioxide. Because of this reaction, carbon dioxide cannot be used to extinguish magnesium fires.
Let's see what's inside.
The reaction products are white magnesium oxide and black carbon.
So what is interesting is that usually when you have a fire, most laboratories, chemistry laboratories will have a fire extinguisher of carbon dioxide. But if you have a metal fire, like a magnesium, burning lithium, you cannot use carbon dioxide because it will continue to burn in carbon dioxide. So basically what magnesium has done is to extract oxygen out of CO2 and reduced it back to elemental carbon. Okay, what about nitrogen-nitrogen triple bond? Can it be broken? Yes, of course, it is being broken every single day in the fertilizer factories, again, by using a reaction that we all learn at the high school level using the Haber-Bosch process. And this bond is actually one of the most strong bond between two identical atoms. It is a 227 kilocalories per mole. Okay, so now let me switch to a simple demo on organic reactions. And again, something that we teach students from the high school level to colleges as well. But my feeling is that the students never get to see an experiment on SN1 or SN2 reactions. So the typical question that we often ask is that if we have these isomeric reagents, isomeric bromides, the primary bromide, secondary bromide, and tertiary bromide, which one of them will react fast in SN2 reaction? Of course, everyone knows that it is the primary. And which one will react fastest in SN1? And again, everyone knows, or everybody has read that it is the tertiary because it produces the most stable carbocation. But the question is, how many of the students actually get to see this reaction? It's in fact very easy to do. And let me show you a video for this. And the question, of course, one can ask is, how do you find out the reaction rates? It's actually much easier to do this reaction than what you may think. And that is because when you realize that SN1 reaction is a reaction of a halide in the presence of a protic solvent, which I will write as R-OH, and it generates HBr. So by monitoring the presence of H plus or Br minus, I can easily monitor the reaction rate. So in the first experiment, what we will do is to look at the relative rates of reaction of the primary, secondary, and tertiary bromide. And the reaction will be done in alcohol containing some silver nitrate, because as HBr is produced in the reaction, silver nitrate will form a precipitate with the bromide, and therefore, faster the precipitate is produced, faster is the alkyl halide reacting. Let's watch the video. This video does not have any audio, so don't worry about the audio part of it. So there are 3 containers, each containing alcohol, and typically you can pre-add the silver nitrate, but in this experiment it's shown that silver nitrate is added to each one of them. So let's finish that fast and add the N-butyl bromide to the first one, and secondary and tertiary to the second and the third ones. And let's see what happens. Pay attention to what happens here, because the tertiary will be added here. All right, so now in this case, seeing is believing. You will see a very rapid formation of precipitate. Precipitate is silver bromide, and it is formed because HBr is produced, and HBr is produced because the tertiary halide is undergoing very rapid solvolysis. And again, I will move this thing. I will do a bit of fast forward, and you can see that even the secondary halide has started to react, but at a much slower rate. The primary does react, but even slower than the secondary one. So this is a simple experiment that very clearly shows the relative rates of reaction of the 3 isomeric halides. There can be another question that one can ask, and that is, if I now have 2 tertiary halides, but with 2 different leaving groups, one having bromide, one with chloride, which one will react faster? Again, most students know that bromide is a better leaving group than chloride, and therefore bromide will react faster. Now, this experiment we will not do with silver ion, because silver chloride and silver bromide have slightly different properties, so we don't want to have any distinction there. We would rather use a pH indicator to look at the formation of H+. Again, a video without audio, and in this experiment, bromothymol blue, I believe, is used as the indicator, RAS, and that is blue in neutral condition, yellow when acid is produced. So on the right-hand side, we are adding T-butyl chloride. On the left-hand side, we will add T-butyl bromide. And let's see what happens when this is added. Notice here that unlike the previous reaction where T-butyl bromide was added to silver-containing solution, here the reaction is not immediate. I hope it will react eventually. All right, it has reacted, but it took some time before the reaction started. And now you see tertiary butyl bromide reacted. It produced acid, which changed the color of the indicator, whereas the T-butyl chloride, which has a poorer leaving group, and it did not undergo the reaction, at least in the time period of the experiment, clearly showing that bromide reacts faster than the chloride. Let me show you this same experiment, which is done in one of my previous in-person experiments. Here again, you see the primary, secondary, and tertiary butyl bromides, which have reacted at the end of the experiment. Tertiary butyl bromide, of course, shows the precipitate. Secondary shows a small precipitate. Primary, very little cloudiness. And here's the other reaction where we use a universal indicator rather than bromothymol blue, which stays yellow when it is neutral, but becomes reddish or pinkish in the presence of acid. And you see with T-butyl bromide, it has formed the color. Color has changed because acid is produced. With T-butyl chloride, the color does not change in the course of the reaction, which is about 2 minutes or so. Again, this is a very simple experiment that any of you can set up in your laboratory, and it gives the students a very good understanding. Now, when we compare these 2 types of reaction monitoring, one using bromide, one using proton, And you would think that the rates will be the same, whether you look at the proton or you look at the bromide, because both are produced as HBr and both are produced at the same rate. But yet, in the presence of silver nitrate, the reaction goes faster. And the answer to that is again something that can be asked to the students, and I will just highlight it here, that silver ion, the presence of silver ion actually exerts a pull on the halide, because silver halide is insoluble. So it pulls the halide and improves or facilitates the dissociation of Rx into R plus and X minus. And that is why in the presence of silver ion, the rates are faster than when you do not have silver ion. Again, this can be done at different concentrations, and it can be developed as in the form of a project. Very simple one. Okay, little more on colors. And this color is about change of color with solvent polarity. And I will again not be able to show the experiment. From my office, it is difficult to set up experiments and show it in real time. But this is an experiment to show that this particular dye called Ricard's dye, it shows a very large, what is called solvatochromic shift. In other words, it shows very different colors with solvents of even very small difference in the polarity. For example, methanol, ethanol, isopropanol, they only differ by a single CH2. But yet, you can see that the same dye giving very different colors in these three solvents. Again, isopropanol and acetone, very closely related solvents, both are polar solvents, but you can see that the color in one case is purple or sort of a violet blue. In the other case, it is green in color. One more image I will show on Ricard's dye with a larger range of solvents, and that is shown here, starting from dioxane, chloroform, acetone, DMSO, isopropanol, ethanol, methanol. You can again see that the ethanol and methanol are showing very different colors. In water, it is not showing any color, and this is simply because this molecule is too nonpolar. It has got a lot of phenyl rings. It's too nonpolar, and it doesn't dissolve in water. Okay, so I will now move on to the next, which is about change of color with temperature, and it's called thermochromism. And this is again, I will show an experiment using a sort of a magic glass, which I got from John Wiley VCH some years ago, or 10 years ago, which was the International Year of Chemistry. And this glass is called a magic glass because this plastic of the glass contains a molecule which changes color with temperature. And let me show a video of this, in which we will put ice water to this glass. Okay. Some ice pieces are there at the top, and you see that it's showing spots of red color. Then we stir, and after stirring it entire, it's not the solution that is turning red, by the way, it is the glass that has turned red. Okay. Because the dye, which is thermochromic, is embedded in the plastic. So now we can show that this change is thermoreversible, because once you take it out, once you take out the water, the plastic, of course, the glass remains red for some time. But then if you add warm water, the water to the level to which you add the water will immediately turn back to the white color. Okay, and the remaining will stay red until it warms up to room temperature. So this is a very simple experiment to show thermochromism. And one molecule that you can actually make in the lab is Ag2HgI4, that is disilver mercury tetraiodide, which goes from yellow to orange when you heat it above 51 degrees. And when you cool it back, the orange becomes yellow again. So similarly, there are copper derivatives of the same complex ion, which can also change color from red to black and so on. There are many such thermochromic materials available. Okay, so I'm now going to show a little bit about spectroscopy related subjects. And this is, of course, you can imagine that this is the picture taken during the sunset, when you see the blue sky and the red setting sun at more or less at the same time under ideal conditions. And as we all study right from high school, that both phenomena are caused by scattering of light. So scattering of light is something that happens when there are particles in the medium which has diameter whose size is comparable to the wavelength of light used. Now, in general, when you have light passing through a medium, three things can happen. It can get absorbed, it can get scattered, and it can be transmitted. If it is transparent, like light going through water, visible light passing through water will not get absorbed or scattered because it will get transmitted completely. Water does not absorb visible light. So in general, again, this is an experiment that can be used to kind of illustrate Lambert-Beer's law, that when an intensity of radiation, I0, radiation of intensity I0 passes through a medium which absorbs the light, let's say this pinkish solution or object absorbs green light, then after it passes through it, the intensity will get reduced to I. And this log I0 by I is governed by the Beer's law or Lambert-Beer's law as epsilon CL. And this is again something that I believe all the master students would know. Another thing that can happen is that the light can be absorbed, but it can be re-emitted at a longer wavelength. And this phenomenon is called fluorescence, which is also part of a spectroscopic technique. And I believe that one of the resource persons will talk about fluorescence spectroscopy in the coming days, in the next 4 days. So I will illustrate this one with a very simple experiment. Again, sort of experiment on the slides. So in this experiment, what we are going to do is to shine green light and convert it to yellow to orange light. And again, you can imagine that this is at a shorter wavelength, this is at a longer wavelength. So for this experiment, what you need are two laser pointers. One is a red laser pointer and a green laser pointer, which are not difficult to get these days. Green is a little more difficult to get. But one word of caution I would like to tell to the students and to everybody else also, that when the laser is on, do not look into the source because it can permanently damage the eyes. Okay, so what you need to do is to have two measuring cylinders, as I show on the left-hand side. In one, you put water and add a drop of milk. It can also be a drop of, milk, a drop of tea with milk. If you don't have a ready source of milk available, or milk powder will also do. The second one, you take a pink highlighter, open it, and dip the tip of the pen of the highlighter in the water, stir it around for a few seconds, and then mix the solution, and it will show a pinkish color. Okay, so now the experiment begins. I would now shine the red laser and the green laser one after another through this solution. And this solution has milk dispersed in water, which makes the water slightly opaque. The purpose of adding the milk is basically to have a scattering substance. So when you shine the red laser, you see that there is a scattering of light and there is a reddish glow all around it, and you can actually see the beam. If you are a clear, transparent, filtered water and pass the red laser through it, you will not see the light beam because it will not be absorbed or scattered. And if I do the same experiment with this solution using the green laser, again, I will see that the green light beam is observed and there's a greenish glow because of scattering. And I would now like to repeat the same experiment with this pink solution. Okay. So first I shine the red laser, and again I see that there is scattering. Okay. Even though there's dye, the solvent red 49, which gives the pink color, which is water soluble, But in the ink, which is put inside the pen, there are other fillers which are used so that the ink can spread on paper, and those things make the solution slightly translucent. And those are the particles which scatter the light. Okay, but remember that in this case and in this case, red light remains red. So that means it's only scattering. On the other hand, now if I take this solution and pass green laser through it, I see something completely different. What I notice here is that unlike the case of scattering, which I have seen here the solution is showing a different color. The green light, which I have seen here, has become now yellow. And that is because this particular dye, the pink dye in the pink highlighter, it absorbs green light and emits in the yellow spectrum. And I'll just show you a quick video clip where through the same solution, I will move the laser pointer and you will see that you can more clearly see that it is yellow in color. Just a few seconds of video. Yeah, you can see that, it's very clearly a yellow laser yellow beam. The laser basically has turned into a yellow beam because of fluorescence. Okay. One more example of fluorescence that one can do is using tonic water. Tonic water contains a quinine, which is a blue fluorescent compound. And what I will show you here, of course, tonic water is used for making various kinds of drinks. We will not get into that today, but here is tonic water under which I have held a shortwave UV lamp, and you can see the beautiful blue fluorescence coming from quinine from this. And one can use a control experiment by taking, instead of tonic water, some other soft drink, for example. For instance, you can even use soda or Sprite or 7-Up, and you show that since it doesn't have quinine, it doesn't show this beautiful glow. Okay, so finally, I would like to show, before I show the last experiment, one example of illustrating FT-NMR spectroscopy. I'm aware that Professor Madhu will talk about it in detail, but I just could not resist showing you a simple analogy. And let me give you a little bit of a background to this. See, in a spectroscopy, basically spectroscopy is when you sort out a property of a molecule or an atom as a function of wavelength of the light. And depending upon which part of the electromagnetic spectrum you are looking at, the property that you measure is of a different type. For example, in UV visible spectroscopy, when you use visible light or UV light, you're looking at electronic energy levels. When you go to IR radiation, you are looking at vibrational energy levels. Similarly, for microwave, you're looking at the rotational energy levels. Whereas in NMR, you're looking at the energy levels of the magnetic nuclei in a magnetic field and use radio frequency. So in an FT-NMR, what is done is that all the nuclei are excited at the same time. And FT essentially stands for Fourier transform. And this is something I would like to illustrate with a very simple example. See, when I was a student, one of our professors actually told us that, our eyes cannot do Fourier transform because what we see as white light, we see as white light. We don't see the 7 colors separately. But our ears can do Fourier transform. When we hear a noise, we actually hear, we hear the noise, intensity as a function of time. But our ears can resolve the frequencies from the intensity versus time into intensity versus wavelength. So high pitch, low pitch sound we can hear differently. And this is something I would like to illustrate with this analogy. Let's assume that we have an object like this, which is a triangular shape, which has, which has a shorter edge on this side and heavier edge on this side. You can imagine that this is actually a molecule having a large number of protons here, medium number of protons here, fewer number of protons here. Okay. Now imagine we have a frequency generator, an audio frequency generator, which can be, for example, a nice piano, which can be keyboard. And typically in a keyboard or a piano, the left-hand side represents a low frequency, right-hand side has a high frequency. So now if I now drop the object I showed previously, the heavier side will hit the high frequency more strongly than the lighter side will hit the lower frequency. Okay, but I will not hear any of the frequencies. When it drops on the piano, I will hear a composite sound. Okay, and let's watch that. It hits all of them. I hear a sound, and what I hear is intensity as a function of time, okay, not as a frequency. So there are frequencies hidden in this one. In the following way, I can show you with an illustration. Imagine that if I have a sound wave of a constant frequency, it will show it like this, and one doesn't decay. If I have two such sine waves of different frequencies, I can get beats of this kind. And if I have more of them, then it will show as this. Okay, so this actually has the information of the frequency which were produced by hitting this object on the piano keyboard. Now, this intensity versus time can be converted into intensity versus frequency by the so-called FT process, or the Fourier transform process. And if I do that, what I will realize is that the intensity versus frequency actually forms a pattern which is similar to the shape of the object. Because here, as I mentioned, higher frequencies were hit harder because this side is heavier. And you see that the intensity of the higher frequency is higher. Okay, so this is a way by which the Fourier transform can be understood and explained in a simple way by showing how this happens when you convert sound, a complex sound, into the simple frequency dependent pattern using the Fourier transform. Okay, so that is as much spectroscopy that I thought I would share today. But very quickly, I would like to show the last experiment, which actually is a very nice experiment, which I always show. And this is about chemiluminescence. What you see here is a firefly, of course. It shows this brilliant flashes of light. There are many other organisms which show this so-called bioluminescence. But chemiluminescence is the general term used for this purpose. And in this experiment, what I typically do is to react hydrogen peroxide, which is the source of the energy. Incidentally, in chemiluminescence, we are converting chemical energy directly into light. And there is no involvement of heat in between. Of course, you can say that chemical energy can be converted to light by, for example, burning a coal or burning a fuel, but there it goes through heat. But in this case, there is no heat involved, because what is happening is that I first form this rather strained dimer of carbon dioxide, which breaks down into a cold carbon dioxide or a ground state carbon dioxide and an electronically excited carbon dioxide. And this reaction is typically done in the presence of fluorescent molecules, which get electronically excited through an energy transfer from carbon dioxide to the acceptor or the fluorescent molecule, and it gets electronically excited. So through the chemical process, you are generating an electronically excited state. And when this electronically excited state decays to the ground state, you generate a photon. And depending upon the energy level between A star and A, you can generate photons of different frequencies. And some of the dyes I typically use are 9,10 diphenyl anthracene, which gives a blue-violet color, robrine, which gives a pinkish color, an orange color, beryline gives you a sky blue or a cyan color, and tetrazine gives a green color. Again, I would show this with a again amateurish video. Good. And please switch off the lights, please. Kill the audio. And I just want to show you that these are the conical flasks in which dichloromethane, hydrogen peroxide, no, dichloromethane, oxalyl chloride, and the particular dye has been kept. And then you will see me adding the hydrogen peroxide, and immediately the color will be produced. Okay, you see the beautiful blue-violet color here, and the yellow-orange color on the solution containing rubrene. And I will not show you the next step because by mixing this, you can show some fun things, but I will do again a fast forward. And in the last two, you will see a cyan color and a green color from the other two dyes. Okay, again, you see that it has produced this beautiful blue and a green color. So you can see that the colors are similar to what I have. As I said, that this was a video taken during a show, not a very professional little one. But once again, I would like you to compare, for example, with two different dyes, I can get two different shades of blue. And again, this has some connection with spectroscopy because, you know, you can understand the emission of these colors by looking at the electronic excited states of these molecules. And here you see an example of all the four solutions that you see together, the blue-violet, in this case, the yellow-orange, the sky blue, and the green color coming from the four different dyes. So that was the last of my experiments. But before I close, I thought I would show you a small video on the life of Linus Pauling. This is primarily to show you that one of the things that Pauling did towards the 1940s was to come up with the structure of alpha helix. And I will not play the video today, but what he says is that he figured out this alpha helix structure. He worked on it for 11 years. He was not successful. And then he was a visiting professor in Oxford, and he became sick. He had to stay in the hospital. And then he was getting bored in the hospital. So what he did is to take a sheet of paper, drew the primary structure of a protein or a peptide, and started folding it. And upon folding it in a certain way, he found that it can form a hydrogen bond between one turn of the helix and the other turn of the helix. And that's how the alpha helix was born. So the message that I would like to get across to you is that he did not give up on the problem, okay? And he worked on it. And so the message to students is that you never give up, even when you are in a difficult situation, such as what you see here in this picture. The other thing is that you should always keep your eyes open because nature presents you with many opportunities, and unless you are ready to take it forward, it will never be yours. Somebody else will be able to exploit it. Another nicer way, perhaps, in which Louis Pasteur has made more or less a similar statement, is that the chance favors the prepared mind. You know, you may get a chance once in your lifetime on a particular problem, but unless your mind is prepared, unless you are ready to take it forward, you will miss the chance. Okay, so at the end, since it is almost 3:11, I would like to ask again the students a very simple question. Okay, you can send these answers to me by email later on. It looks like a very stupid question. Okay, the question is, I give you chemically pure sodium hydroxide, chemically pure potassium hydroxide, and I want you to make 1 liter of approximately 1 molar or 1 normal equals sodium hydroxide solution, and 1 liter of approximately 1 molar or 1 normal equals potassium hydroxide solution. I say approximately because, you know, sodium hydroxide and KOH are not primary standards, but I'll give you the chemically pure samples. Okay, so I need to know how many grams of KOH, how many grams of NaOH you require. Okay, so that's a question. So before I close, I will just take a couple of minutes to highlight some of our own research activities. In the last few years, in fact, we have been doing a lot of spectroscopy, particularly fluorescence spectroscopy, using a kind of semi-solid or semi-liquid materials, which are called gels. You see gels in food industries, in cosmetics. So these gels are made by mixing this particular biosurfactant called cholic acid and various types of metal salts. So we have made, as you can see, that these are small bottles which are turned upside down with these gels. The gels don't fall. So that's one test that you have formed a gel. So we have been using these gels for various kinds of activities, and I will skip most of the slides. We have also made various types of lanthanide gels, which are again photoluminescent. And using these, we do enzyme sensing, drug sensing. For example, let me show you this. Very recently, we have figured out that you can actually detect some of the antioxidants which are found in green tea, certain drugs at very high detection sensitivity, a variety of enzymes such as lipase, glucosidase, beta-lactamase, alpha-glucosidase, alkaline phosphatase. And very recently, we have also worked out a way by which you can detect formaldehyde, hydrogen peroxide, and water present in organic solvents using our photoluminescence methods. And we have also developed through a company, I think I don't have that picture today, a small handheld, not handheld, it's a portable device for looking at this photoluminescence and measuring the concentration. So much about my own research. But basically, I thought what I described in the last almost 70 minutes is that you can plan organizing experiments around the themes that you teach in the lectures. And sometimes if you can connect the lecture with an experiment and the experiment with some real life process, then the understanding of the students will be more complete and they will be better prepared to face the real life once they graduate from their respective colleges and universities. What I showed today are only some representative examples, and I'm sure that each of the teachers can think of more such examples of experiments that you can do to sort of reinforce some of the principles that you teach in the class. And by seeing something in real life, the students might get a better feeling, a better understanding, and a better appreciation of what they study in the theory lectures. Before I end, I always do a little bit of fun thing, and today is no exception. Since I talked about the periodic table to some extent, I would like to play a periodic table song. Many of you have heard this song before. It's called Elements Song, and it was developed by a mathematics professor named Tom Lehrer, who was a mathematics professor it was composed, not developed. It was composed by Tom Lehrer, who was a mathematics professor in Harvard University. And a clip that I'm going to play is in fact from 1967, when Tom Lehrer sang this song in a meeting in Copenhagen. Okay, so it's twice as interesting because he himself is singing the song. So let's hear this one.
Now, here's a song I always get requests for, but I can't understand for the life of me why. It's simply the names of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. We'll try. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, plutonium, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. I left out one, actually. A new one was discovered since the song was written. It's called Lawrencium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium, manganese and mercury and molybdenum and magnesium and dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, magnesium, titanium, tellurium, and cadmium and calcium and chromium and curium. And there's gold and californium and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, kryptonium, radon, xenon, zinc, and rhodium, and chlorine, copper, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
I hope you have enjoyed the song, which I always find is very entertaining. And you can get the lyrics from by searching it on Google. Called you just search for Element Song, and it's a bit of challenging to try to sing the song because it's very, very rapidly done, and you have to follow the order of the elements in the correct way. But the students can give it a try. So with this, I would like to conclude, and I do hope that you have enjoyed and appreciated some of the experiments that I showed. And sometime in the once the virus eventually disappears, we might be able to do these experiments in person. And I look forward to such a day. So once again, thank you, Dr. Ashley, for giving this opportunity to share some of my thoughts with this virtual audience. Thank you very much.
Thank you, sir. Before concluding, I would like to ask participants, if you have any questions, Uday sir is ready to answer. Participants can unmute yourself and you can ask a few questions.
Okay. Yeah,
Any
I don't see any.
Yeah. Even in chat box, we didn't see any questions. I think sir is very clear, and he made us all enjoy this session with his very visualized explanation. So now I'll move on to vote of thanks. So on behalf of Ramaya College of Arts, Science and Commerce College, so I would like to thank, first and foremost, I would like to thank Professor Uday for spending his valuable time in experiments and very beautiful explanation, sir. Sir has explained from basic experiments till spectroscopic techniques he explained, and all the faculties and students have enjoyed it a lot. So I thank you very much on behalf of our college and department for spending your valuable time with us, sir. I also thank Professor Shiva Prasad, who has joined this session. So on behalf of our department, I thank Professor Shiva Prasad for attending this session also. And I also thank all the participants, faculties and students from at national level. We have participants from different colleges. So I thank you all for your valuable presence and attending this program. So feedback link is posted in the chat group, and please fill the feedback session. And I request all the participants to join us for the upcoming sessions also. Thank you, sir. Thank you very much.
Thank you.
Thank you, sir. Thank you, ma'am.
Thank you, Uday sir, for accepting the invitation. And thank you, Vibha, for moderating the session. Thank you all.